Last topic is a selection problem. In part B, I will talk about that. Okay, so I will talk about that at some time. But here, let me do that Mergesort first. The selection problem. When I find some time, I have 15 minutes. I will first talk about the selection problem question. Then I give you the conclusion, but I do not go through the solution, how to solve it. That's too long, and that will usually, very hard to understand. Okay, very hard to understand. But I just give you the conclusion. All right. So that's the selection problem. All right. I will. So Comac. So I will do that later. Just try to remind me. So if I miss that part. But I will do it before we end module 4. Module 4 we have part D, the quick sort. Before I end module 4, I will talk about that selection problem. Okay. All right. So let's continue our introduction, C.1, Mergesort. Problem number 13, merge two sorted arrays. So we consider a small computing problem, merge two sorted arrays. So the question is why we want to work on this question. What's the reason behind it? So here, there is some reason. So let me describe the background for this question. All right, first, the question description. Given two ordered arrays, how to merge them to get an ordered array. So merge two ordered array, we want to get a larger ordered array. The whole array must be ordered. So we merged those two. The question is, we want to find the best solution. Best possible solution. Okay. Not the best case, best possible overall solution. Okay. All right. The motivation here, let me just describe a very special situation where we need to use this resolve this problem. Okay. So let's consider this question. How to sort a huge array. Still sorting, but the data is special. How special is the data? The data array is huge. How big it is? Here, let me describe how big it is. I use this line segment to represent this whole array, very big. You can imagine this array is so big, it is stored on the hard drive, but the whole array cannot be loaded into the memory completely. We know our memory is much smaller than hard drive, right? Look at the current typical memory size for a laptop. Let me just use this 16 gigabytes. How about that? My laptop, I only have 4 gigabytes. Okay, very small, but it's good enough for my teaching, right? So here, I just assume 16 gigabytes. Pretty big, right? But look at the, hard drive. Hard drive, some students may have the terabytes, right? So here I just assume 500 gigabytes. You can see much bigger than the memory size, right? Here we assume our data can be stored on the hard drive, but it cannot be loaded completely into the memory. Okay, under that situation, can you sort that array? We know when we implement our algorithm, we need to load the data into the memory, usually, right? Yeah, because otherwise, how do you execute your program, your data on the hard disk? Yeah, all right, so here, to solve this problem, we need to find a special way to do it. Okay, yeah, so here, let me describe the way to do it. Yeah, we use divide and conquer way to do it. We want to break this huge array into smaller pieces. Yeah, all right, yeah, like this. Yeah, and each piece, we can load it into the main memory. Yeah, so we can do that. Yeah, each piece, we can load it into main memory, okay? In that way, we can sort each subarray piece by piece in ascending order like this. Okay, yeah, ascending order. Yeah. But you can see the whole array is not sorted, right? Yeah, we conquer individual subarrays, but the whole array not sorted. In this situation, we need to merge two sorted arrays and to get the whole array sorted. Yeah. Here, yeah, because when we break the big array into smaller pieces, we can do parallel computing, right? We can send each subarray to one parallel processor, right? Yeah, so that means, using this way, we have many use cases for this special divide and conquer way, okay? Yeah, but at the end, you need to merge two sorted arrays. That's the problem we are working here, our problem number 13, okay? Yeah, so that's the background, motivation, for this question, yeah. Next question, how to merge two sorted arrays? Yeah. So we need to solve this problem. It's not hard, but we want to go through the analysis work, okay? All right. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements? Yeah, so let's work on this new problem. Yeah. But when we work on it, we do not want to start from scratch. We want to use our old experience a little bit. Now, we want to borrow our old experience. Yeah. In that way, so we can get a better understanding. Yeah. Here, we want to take advantage of the structured data. What's the structured data? Two subarrays are sorted. That's the structured data. Yeah. So we need to use that property. Yeah. Ordered property. Okay. Yeah. All right. Okay. All right. So now we have learned several sorting algorithms: selection sort, bubble sort, insertion sort, right? Yeah. In those sorting algorithms, some of them do not take advantage of the order information. Yeah. Look at the selection sort. Do we take advantage of order information in the selection sort? No. Because no matter the order, what order is, ascending order, descending order, your selection sort uses the same number of comparisons. Now, best case, worst case, the same number of comparisons. that means you do not take advantage of the order information. Okay, the bubble sort also, you do not take advantage of the order information. Yeah, yeah. But here I remember once before, one student sent me an email. Yeah, because on our textbook there is a modified version of the bubble sort. Yeah, after every round scanning processing, it checks if there is any swap operation. If there is no swap operation, then it stops. The algorithm stops. Because no swap operation, that means it is already sorted. Okay? You do not need to do further scanning. Yeah, that's the modified bubble sort. It is described in our textbook. All right? Yeah. So that student make this argument. Based on this algorithm, we take advantage of the order information. Yes, it's true. Yeah, it's true. Okay. Yeah. In that modified version of bubble sort, we take advantage of the bubble sort, the order information. Yeah. All right. Okay. Yeah. Here, when we look at the insertion sort, do we take advantage of the order information in the insertion sort? Yeah. If we recall, if the data is in ascending order, here I'm talking about insertion sort. Okay. Yeah. If the data is already ordered, then the efficiency is big O of n. If it's not ordered, worst case, big O of n squared. That means the ordered information really helps us to improve the efficiency. We can do much better with ordered data. All right, that means this insertion sort takes advantage of the order information big time. Yeah, really big. All right, yeah. That means we can borrow the idea of this insertion sort and try to solve our current problem. Well, because they are related. The insertion sort and this merge operation, they are related. Yeah. Because mainly on the order information, how to take advantage of order information to improve the efficiency. Yeah. All right. Yeah, so after that, okay, yeah. Now let us work on the first, let's recall insertion step. Okay, from insertion step, we want to modify it a little bit to make it the merge step. How about that? Yeah. So we start with the insertion step. After that, yeah, so we need to make some modification. Then we try to find a solution of the merge operation. Okay, all right, so let's look at that insertion step. Yeah. All right, so let me still use the diagram. Insertion, we have a ordered array. This is ordered array, and a new key V, we want to insert it somewhere in this ordered array. Okay, so then we do comparisons, find right location, and then we make shift operations, then we complete the insertion. Yeah, remember that, right? Yeah. So that insertion step, yeah. Can we look at that insertion step in slightly different view here, right? Yeah. Can we change our view a little bit here? Yeah. So here we treat This one key element, can we treat it as one element array? It is special array, right? It is an array, but it just has one element in this array. Okay? One element array, and it is sorted, right? Think about that. One element array, it must be sorted. All right. Now, can we treat that insertion step as the merge step, merging two sorted arrays, right? But just the smaller array is a special one element array. Yeah. So here you can see the difference between our insertion operation and the merge operation is the merge operation is just a general version of insertion operation, right? Yeah, a general version. Yeah. Make that one element array to multi-element array extension. How about that? Okay, make that kind of extension. That's the relationship between these two operations. Okay, yeah. All right, yeah, so sorted. Or we can say our insertion operation is just a special case of the merge operation. Okay, so you can see the relationship. Yeah. All right. So the new interpretation, two sorted arrays are combined to get a new sorted array. Yeah. But just the one is a special, has a special structure. Okay. Yeah, we can make it a little more general. Yeah. So that's the, this new view, merge two sorted arrays for a new sorted array. That's the merge operation. Look at that. So insertion operation is a special case of the merge operation. Okay, yeah, all right. Since we have solved the insertion operation, so we try to use the similar way to solve the merge operation. Okay, yeah, all right. So let us apply the new merge view. Okay, all right. The new merge view for the insertion operation, we merge two subarrays with data sizes k and 1. Okay, yeah, k and 1. Yeah, it's not balanced, right? Yeah, because the difference is big. Yeah, and the data distribution is not balanced. Remember the data distribution thing, I talked about balancing principle before. Yeah. Look at that, the balancing principle. When we study the binary search, we observe some balancing principle. If we make data distribution as even as possible, we will get better performance. That's the balancing principle. Yeah. But here, if we use the insertion way, the data distribution is not balanced. Yeah. So that means its worst case won't be good. Yeah. Yeah. It may have a good best case efficiency, but because your data distribution is unbalanced, so you usually, most of the time, you won't get a good worst case efficiency. Right? Yeah. So here, for our new sorting algorithm, we want to have a good worst case efficiency. Yeah. Insertion sort, the worst case efficiency is bad, big O of n squared. We are not satisfied with this one, so it's not good, right? It's a bottleneck, too slow. Yeah. So when we consider a new sorting algorithm, we want to greatly improve this worst case. Big O of n squared, worst case. Okay, yeah. So how to improve? In our data distribution, we want to make balanced data distribution. That's the main arrangement we want to do here. Yeah. All right. Yeah. So yeah. So poor worst case. Yeah. Improve by balancing principle, we try to make two subarray of equal size, as equal as possible. We may have one difference, because when you have all the number of elements, even you try to break it evenly, we end up with two subarrays. One has one more element than the other. That is fine. Only one small difference. So we just take it.